Hello, welcome to my presentation, which is designed to answer the question we had here. And as you have seen, in NMR we have a spin Hamiltonian, so that's perfect to get quantum advantage. And if you want to have that, well, you have to beat me and my team. And I want to show you that I will make your life as hard as possible, virtually impossible. And so I'll show you what we have done, what we've implemented, and at the end, where there's still some room for quantum advantage. Okay, so this is basically how to solve that problem classically. Now, this is a theory talk, so of course on the first slide I have to have the Hamiltonian, and Peter already explained it. So we have the, let me see, no. In the Hamiltonian, we have first the coupling of the B field with the nuclear spin. And the important quantity here is the gamma L, that's the gyromagnetic ratio, and that gives you the coupling strength of the nuclei with a magnetic field. And if you look at the numbers here, these numbers are pretty big. This is already a problem for numerics, where you have to be careful. And of course, for the quantum computer, in that way, it's a no-go, because you cannot do time evolution over times that would be 10 to the 7. But that can be solved with a rotating frame, which I will explain later. Then we have this delta L, the chemical shifts. Those are basically the differences we have for the different nuclei if we have different chemical environment. And finally, we have this JKL, which are the coupling between the spins. And we already had that in the last presentation. And well, that's how it looks like. We have peaks. The peaks position in principle give you the chemical shifts, and the multiplets are the J couplings. Of course, things get more complicated if the multiplets overlap, which you typically will have in a low field spectrometer. Now, how does the experiment actually look like? So first, we have to prepare everything to put your sample in a tube. You put it into your spectrometer, and then you apply a pulse. So basically, you have prepared it, you apply a pulse, and the pulse means you flip the spin from here to here. And then it just starts to process in the magnetic field. So that's basically, so here we flip it, and then it processes. And we just record then the magnetic field that we get from the precession of the nuclei. And over here I've written basically the typical pulse for where you can rotate it by 90 degrees. And that's basically the very simplest NMR experiment what you can do. However, there are millions of different ways what you can do. You can change your pulses, you can actually do several pulses, and there's a lot of other things. But here I will restrict myself to the simple 1D NMR spectrum. And now the question is, how can we actually simulate this? First, for the pulse, we will not simulate the complete time-dependent radio frequency signal that you shine in, because at the end, the only thing it does, it flips the spin. So we really apply only this rotation operator. And that's it. And what we have then to measure is, we measure just the expectation value of the magnetic field from the processing spins. Okay, and that's just the spin, Ix, or also Iy. Typically you measure both, and multiply it again with the gyromagnetic ratio, because that gives us the coupling of the spin with the magnetic field, also vice versa when the spin rotates, the strength with it radiating. And well, then we have the time evolution for the density matrix, just the standard harmonic equation, and that's it. And that's what we have to calculate. Now, if you calculate NMR, you typically do not calculate this expression, the complete one with the density matrix, but you do evaluate something much simpler, and that's a spin-spin correlation function. And I just want to show you how you actually get from this expression to the correlator, because there's sometimes confusion how this is done. Because at the end, the formula you get looks like it would be a linear response, but it's not linear response. You hammer on the system, you flip it completely. There is no small parameter. It just happens to look like it would be a Kubo formula, but it's not. Okay, so here I've just repeated everything I said so far. We have the Hamiltonian. We want to get the trace over Ix times the density matrix. And then the density matrix is basically we start at T0 at the beginning. We have a thermal distribution. And then we flip the spin in the XY plane, and then we have the precession. And now we just calculate that. And now what we do is we do a high temperature expansion. And so we have just a Boltzmann factor, and we expand it in first order temperature. Now, the first term we have just the normalization, or the 1. And if you look at this formula here, if you put the 1 in here, and then we have the expectation value of Ix, this will be 0, because Ix is S plus plus S minus. It changes the SZ quantum number. Our Hamiltonian preserves SZ, so this is 0. So we need something that flips it. We need a combination that we have an S plus S minus. So we need the next term, and then that's basically what we have here, the Iz term here. And then in principle we also have that term, but this is always thrown away because the gamma L is 10 to the 7, and this is just a few hertz. You can keep it, but it's you will never see it in any numerics. And then we take this as rho naught, and we plug it just in here. That's the next step. So then we can also, since the density matrix is now just the Iz operator, and please, the density matrix is of course not the Iz operator, because that would be not positive definite, but we are only interested in the deviation from the 1, which does not give you any contribution. So this is the leading term that gives you a contribution. And then we have here, this is just the Z, and that gives us the Iy if it's just rotated. Note, if you do the math correctly, rotating in the I, that you get the Iy operator is only strictly true for spin 1/2. If you do this for higher spins, you get actually correcting terms, which are a little bit nasty. And the delta L is typically also omitted here if you look in textbooks, because it's of the order of ppms. If you want to do plutonium 239, then it would be of the order of 20–30%, but that's not usually done. Now, why is this approximation valid? Well, you have to keep in mind the energy scales are pretty low. We are talking about fields, so let's say 7 Tesla. If you multiply it with a gyromagnetic ratio, this is over 300 megahertz, and this corresponds to 15 millikelvin. So every experiment above 1 Kelvin is in the high temperature regime, and this is usually done at room temperature. So actually, and that's a problem with the sensitivity, the imbalance we have between up and down spins is of the order of 10 to the minus 5. And it's only this imbalance that we are measuring, and that's a problem with the sensitivity of NMR. Okay, so now we have basically, if you put everything together, we have the correlator in the time domain. And I've also added the theta function here because you don't get a response before you have hammered on your system. And you actually need it for causality, for proper Green's function. And now this is all pretty standard, what you can find in textbooks. What we do basically different than all other solvers is we are not solving the system in the time domain. We directly go to the frequency domain. So we just have to Fourier transform it. And then as usual, we need this convergence generating eta. Otherwise, the Fourier transform would not converge. So we have this I eta here. And then if we just plug in everything in, and since we have to go, I mean, we are in a very high temperature regime, it's not ground state, we have to sum over all states in the system, then you immediately get just this expression here, which is nothing but this one Fourier transformed and explicitly written down as matrices. And remark, everyone typically just skips over this I eta as a convergence generating factor, but actually what it does, it summarizes everything we have from the limited spectrometer resolution, any noise we have in the system from the nuclei and especially from the solvent, that's all put into this simple eta. If you want to do it on a more rigorous way, you could also do some Lindblad equation. And you also need it that you have a Kramers chronic and that you have a proper causal Green's function. And last thing, we have to be careful is gamma L here from the response. The derivation is completely correct. The only problem is usually that's not how experiment is done. I told you that we look like a hammer, delta function like, that we put on the system. But typically, if you have a heteronuclear system, let's say you have phosphorus and hydrogen, then you only typically flip one of those. Because since gyromagnetic ratios are so different, and you have to put your pulse, you never have a delta pulse, you really have it as a wave packet, and this wave packet is a delta for the hydrogen, but not for the phosphorus. So if you want to flip both, you actually need two different pulses. Usually you cannot combine it in one because the frequencies are so vastly different. Okay, so we have that. Now, as I said before, we have a problem with this large numerical values of the gyromagnetic ratios. But that can be rotated away in a simple way, namely we go in the rotating frame, and that is basically we go on the measurement like the unshielded hydrogen rotates. And this is the transformation we apply. And if we put everything together, so we transform operators and wave function with that. Then if you look carefully what happens, well, if you have this S plus, that means you flip the down. So you have basically the rotation of I minus I omega RT. Omega R is the reference frequency. Typically we just take the bare proton frequency. And then you have omega R half from the Z operating on the downspin. And then you have acting on the other side. So you get here one half, you get here one half. And at the end, S plus gets a factor of minus I omega RT. And the same is for S minus, just Hermitian conjugated. And as Z commutes with U, so that's unchanged. And if you look what happens to the Hamiltonian, S plus, S minus is then just unchanged. So this doesn't change the form of the Hamiltonian. However, you have to look at the Schrödinger equation, and if you take the derivative of U of t times psi, you have the product rule, and at the end you just get this additional term for the time evolution. And that means at the end you can basically add your frequency omega r here to this term. And if you want to, you don't have to set it precisely on the bare hydrogen frequency, Larmor frequency, but for instance, on a quantum computer, you may want to shift it so that actually this one is as close as possible, spread it around around 0. So you can play there a little bit. Of course, at the end, if you want to plot your result, you have to make the shift backwards. Since we're typically plotting the ppms anyway, we anyway have to subtract the proton frequency. So that's how we get rid of the large numbers. The next thing is we actually apply a nonlinear grid. Since we are solving for each frequency point, we are not restricted having to a linear discretization as you would have just if you do a Fourier transform of the time signal. And the way we do it, first we just take the spectral function as given by the chemical shifts and a very broad Lorentzian around it. And then we do an equal area discretization. That means we look that each frequency point gives the same area that we have. Then we have a discretization and we do first of all. Okay, and then as we have here only a few points where we anyway don't have a signal and we have a very high resolution actually at the peaks. And this helps a lot if you have very sharp peaks, and many of them. Still, the algorithm scales exponentially hard. So it's actually 4 to the m, if m is the number of spins, because we have to work with a full density matrix. And as a side note, the diagonalization that we need, the full diagonalization, is not our limiting factor. The limiting factor is actually the expectation values we have to calculate at the end of these matrices. If I go back, problem is not getting the diagonalization. What costs the time is actually to do all these sums. Because this is also power of 3 of the dimension, but it's many of them. Diagonalization is not the time limiting thing, it's the summation that kills us at the end from the time that we need. Okay, so since we have asset conservation, it's the largest cluster we have to solve is if m is a number of spins, it's m over m half, because that's how we can just have m half up particles and the z of down particles. And this is exponentially scaling, so we have to cluster the Hamiltonian. So here's camphor, and then we can just take two clusters, we solve that cluster and that cluster independently. And if we have, for instance, a hydrogen here, then this is a good clustering. And actually what we do is we calculate the spectral function for each hydrogen separately and sum them at the end. And the reason why we do it, well, this cluster is very bad if you want to calculate the response for this hydrogen, because this is influenced by those here. So we should actually have a cluster that goes like that. And that means precisely what we are doing. For each spin, we have a different clustering. And if spins happen to be in the same cluster, of course, we solve that cluster only once. And then we solve all these clusters, and at the end, we sum everything together. And now it scales only with the binomial of the cluster size. Now this, of course, you can do. The question is it a good approximation? And note, for those who have seen our archive paper, we have changed a few small details in how we actually do it. So the results we now have are nicer than those we published in the archive paper. So there will be an update soon. Now here's the NMR spectrum of camphor and the zoom in. And what you see here is just the cluster sizes that we have chosen. And you see you don't see any difference here. Now, this is where it works nicely. But are there actually hard tests, complicated molecules? Well, our competition is spinach, that's from the Ilya Kuprov's group. And we went to the examples, and the folder is extremes, phosphorus cluster M. Extremes because if you look into the description there, it tells you it takes many hours and more than 128 gigabyte of RAM. And all what we present here is done on these kind of laptops here. So here's what they called phosphorus molecule, the comparison between the result we get for different cluster sizes, where you barely see a difference in our result, and then compared to the green line which we get from spinach, so we actually get the same. And note this is a one where we have 27 hydrogens and 7 phosphor atoms. Here's actually what's also interesting is the experimental curve. And on every level that makes relevant, there is no difference. This is the same curve. And we just take a few minutes. We don't need hours to calculate it. And the reason is basically that we do everything in frequency space, and having this implemented in a performant way. And another example, that's a comparison with the experiment on the right side. And this is actually the molecule, but I guess this information is useless. I mean, it's some strange cluster, which only is there because it's complicated for solver. And the other one is D-phosphane. That's also from the extremes folder from spinach. And this has two interesting, or two regimes where one sees peaks. And here you see the scaling. So we get the main peaks correct already with a cluster size of 8. We get this one in the middle, in principle, from the shape correct. The file structure is not correct because every time we make the cluster larger by 1, we get basically an additional peak in the multiplet, and then we have this odd-even effect. So only every second one is really in the correct phase where it should be. Otherwise, it's just shifted by in the middle, and then it's correct again. Now, this one is very hard because to get it correct, you really have to solve the 22-spin problem completely. Now, if you do the math, this is already pretty large. The way we can do is solve this actually is, this has a lot of symmetries, and we combine all of those as a spin 9/2, and we go through to all the Clebsch-Gordon coefficients, split them, and sum that up. It's not hard, but it's very tedious if you want to implement that. It's just annoying. But it can be done. So, and again, this was done on a laptop. We can do it in 10 minutes, the full solution. And Ilya Kuprov, the code needs a few hours, and I think they even used some GPUs for it. Okay, that's it. That is the second regime where you see a peak, but it's basically the same. We get it already for small clusters, in principle the shape correct, which is basically all what you're interested in, and the fine structure gets pretty good already for 11 sites in a cluster. But to have it completely correct, you need all 22 spins. And then, I mean, up to here, I would say there is no room for quantum advantage. We have the system completely under control. You really would have to look for something very, very special if not solve it. But there's one regime that we currently have not under control classically, and that's zero field. And zero field means we have no magnetic field here, and that this term drops out. And that means what we need for the clustering is we need, of course, a large and a small energy scale, and we make precisely use of these large gamma L's, and this is gone now. Now, if you only have hydrogens, you can solve it analytically because this is SU2 symmetric and the solution is just a peak at zero frequency. If you have heteronuclear systems, then the point is you are not measuring SZ, but you are measuring gamma L SZL. And if you have different gamma L for different spin, then it's not the complete SZ you are measuring, and you cannot solve it trivially. So you really have to do the calculation. Now, how do you actually do the experiment if you don't have a magnetic field? And there are two variants. One is you prepare the system in a magnetic field. For instance, you let it fall through the magnet, and then you measure it in zero field, and you apply the pulse in zero field. Or the other thing is you do everything in zero field, but you polarize your system, for instance, by putting some polarized hydrogen to it. But then you really have to measure the complete density matrix, because you are not starting from a Boltzmann distribution. And note, since you are zero field, this one drops out. There's no need for a rotating frame. I mean, you're really measuring something of the order of a kilohertz response. And well, here's an example how it looks like. That's basically from a publication here. That's what they did with a calculation. They have a calculation where they have artificially done a smaller broadening and the experimental curve, and that's what we get. So we get basically we get the same as so, which also shows you that our solver should be correct in this regime. But here really currently we have to solve it completely because the clustering doesn't make sense, because we don't have this separation of energy scales. And with that, I'm at the end of my presentation, and thank you for your attention.